So, hello, my name is Raphael Bild. I'm from Technical University Munich, and I'm going to present you the paper SafePub, a truthful data anonymization algorithm with strong privacy guarantees. Is it better? So, well, I will begin with giving a little overview about some different areas of research in which technical measures for data anonymization and privacy protection are being developed.
Sorry. You need to speak up slowly and closer to the microphone, please.
Okay. So first I'm going to give a little overview about some different areas of research in which technical measures for privacy protection are being developed. The first area is statistical disclosure control. These are methods which are being frequently used in the field of statistics, and they're usually not primarily based on formal notions of privacy protection, but rather on informal rules, which are rules of thumb, which are based on experience and which are being reviewed by experts. Methods which are common in that field include random sampling, so that you can take some sample of a data set, modifications of data, summarizing information, and also perturbation of information, which means that random noise is added. Then a different field of research from computer science has been developing syntactical data anonymization methods. In this field, syntactic models which pose strict syntactical requirements for formalizing privacy protection have been developed. Methods for achieving these formal privacy models include the generalization of attribute values or the suppression of attribute values. There have been a multitude of such privacy models suggested in the literature. The most common of them is k-anonymity, which requires that each record is indistinguishable from at least k-1 other records. Then some drawbacks of the privacy protection degree provided has been detected. Then other models which try to overcome these issues have been developed, such as L-diversity and T-closeness. And so while these models provide some formal degree of privacy protection, they are not without drawbacks. These models are typically achieved via data anonymization algorithms. in which strict limits by these privacy models are imposed, and then within the bounds of these constraints, data quality is maximized, which is then measured by according quality models. Now finally, differential privacy is a comparatively new approach for formalizing privacy protection. And this is now not a property of a data set, but it's a property of an anonymization algorithm. It provides a strong degree of privacy protection, and the basic idea of that model is that the addition or removal of one record from the input data set does not affect the output of a probabilistical algorithm by much. So in the sense, the intuition behind the privacy protection is that you are safe to contribute your data because no matter what will be revealed by any analysis will not be much influenced, and hence the consequences for you personally will not differ drastically. There has been, let's say, quite big research from a theoretical perspective, and it's also being increasingly applied in practice. For example, Google and Apple have been developing and deploying differential privacy for collecting user statistics in a privacy-preserving manner. Methods which are common for achieving differential privacy are the Laplace mechanism. This is also a perturbative method, which adds results drawn from an appropriate Laplacian probability distributions to the results, or the exponential mechanism, in which different possible outputs can be assigned different scores, and then a specific probability distribution is used to select one of these solutions in a manner which assigns higher probabilities to results having higher scores. Now at our institute we are developing a software called the ARCS data anonymization tool. That is an integrated tool providing a GUI as well as an API. It comprises various privacy models and quality models and different transformation techniques. And it supports an iterative way of performing data anonymization. So first you can configure your privacy models and the privacy constraints and perform the data anonymization. Then you can explore the output data, then perform various risk analysis using different models, quality assessments using different models, and then in turn adjust your configuration to try to optimize the anonymization process. So up to now the methods included are mostly from the syntactical anonymization side. The tool is focused on microdata release, so the output is really a data set that is an anonymized version of the input data set. That has many advantages because when you have a data set which is safe, you can perform as much analysis in the data set as you want. So it provides quite some good degree of flexibility. And another thing that is focused by ARCS is truthfulness of methods. That means that methods should be not perturbative, but that the output data should be truthful and semantically consistent with the input data. That is also helpful for many analysis and is also appreciated by many analysts. And the challenge which we have addressed is now to integrate differential privacy in that tool in a way that it produces truthful microdata and that it integrates well with the existing methods we have implemented for data anonymization. So in the literature there has been some previous work on how you can achieve that, and most notably Lee et al. Have suggested some connection between random sampling, k-anonymization, and differential privacy. That is, when you perform k-anonymization and proceed it with a random sampling step, then it satisfies a notion of privacy protection that is epsilon delta differential privacy. That is a model that is slightly weaker than pure epsilon differential privacy, but it has been shown that this sacrifice, let's say, in terms of having the delta, is necessary, the price to pay for attaining truthfulness. So up to now that method had been studied purely from a theoretical perspective, and the focus was on how to derive the parameters for the data transformation, how to take parameters for the data transformation and derive from that the resulting privacy guarantees. That is epsilon and delta. So here beta is the sampling probability. That means that during the sampling process, every record is individually selected with a probability delta or dropped with a probability 1 minus beta. Then the parameter k is used for k-anonymization. That means that in the end, after a generalization scheme is applied, which replaces attribute values with more general values, then every record is removed which appears less than k times. So in order to put that mechanism into practice and to integrate it into ARCs, there were several challenges that had to be overcome. These are illustrated here on this slide. So the first is that it is not obvious when you have the privacy parameters, epsilon and delta, how to derive the parameters for this data transformation from them. Then also the generalization scheme, that is the concrete strategy for using to generalize attribute values. It is not obvious how that should be selected, how a suitable such scheme can be selected while still satisfying differential privacy. And finally the question is, how can you optimize the data utility of the resulting output set towards specific analysis, towards specific purposes. So a little bit of information about the challenge one. Here are the formulas that have been suggested by Lee et al. So here the connection between epsilon and beta is fairly straightforward, it is easy to revert. But here we have some sequence for which the maximum has to be determined, and that sequence is non-monotonic. So that is a difficult task, and Lee et al. have stated in their paper that they were not able to find an easy and close expression of that form. So for solving the challenge, we have introduced an upper bound here and used that for determining the maximum of the sequence. That was a key challenge that had to be overcome in that implementation. Then the selection of the generalization scheme we have modeled by basically performing iterative applications of the exponential mechanism. So we go through the set of all possible data transformation schemes. For each one we determine what is the possible output quality, and doing that we then set up scores which rate that solutions and draw among them with the exponential mechanism. And we do that in an iterative manner which kind of greedily transfers through all the set of possible solutions. Then to guide this traversal to concrete quality models, we have developed score functions which are attached to 5 general purpose quality models, and we have developed one more score function which is designed towards optimizing output for a concrete analysis task, that is statistical classification. Then we have presented evaluations of the method, because now we have quite a few parameters which can be used, and we have performed evaluations primarily also to determine recommended parameterizations. So regarding the number of preserved records, that is the records which actually come into the output data set, we have tried several values of epsilon and determined that an epsilon value of around 1 gives a, let's say, good compromise between privacy protection and enough information that is still retained. Then regarding the search strategy, there is a number of iterative applications of the exponential mechanism. This is steps that we have researched against the against the privacy budget that is to be used for each application. That is this parameter epsilon search. And here we figured out that the number of steps kind of leads to a more or less monotonic decrease of information loss. So a higher number of steps is good, and about 300 was a value when no much more change could be observed. For the privacy budget, we have determined that that numbers in the order of 10 times minus 1 kind of go to a good value. So quite low numbers are sufficient here for performing the search. And regarding delta, we have found in the literature the recommendation that it should always be selected depending on the number of records, so that it is smaller than 1 through the number of records in the input data set. So we found that this is a suitable parameterization that can be used. Moreover, we have performed a comparison with related methods. The most related method is an approach developed by Fouad et al. That is quite similar in the sense that this is the only other method for truthful microdata release that satisfies epsilon delta differential privacy we found in the literature, but we figured out experimentally that actually the privacy guarantees, if you want to have really provable privacy guarantees, then the amount of generalization is very high, so that in practice that method was not really feasible. Then as a next step, we compared it with epsilon differentially private methods, which on one hand have a bit stricter privacy guarantees, of course, because it's epsilon delta, but on the other hand, these methods are then perturbative and don't satisfy truthfulness. For this, we have compared our approach with 5 approaches here in the literature. We found that in most cases the results are comparable, and in some cases also our method could outperform state-of-the-art methods. The most related of these approaches now is diffgen, and we found that also it has an iterative search strategy which is quite similar to ours, but it can be seen that this method is not only non-monotonic, so in the sense that the higher the number of steps is, you can't say that the quality will automatically get better. So in this sense, it is more difficult to parameterize in our method. And also the output quality was in many cases lower than that which could be achieved by us, even though that satisfies epsilon differential privacy. So details about all that you can read in the paper. So, time to come to an end. To conclude, we have developed now a practical implementation of truthful differentially private data anonymization, which has been evaluated in practice and which can outperform state-of-the-art methods, or at least compete with them. The method is conceptually rather simple and easy to parameterize. And there are various lines of future research. For example, I have to say that the transformation scheme that we use at the moment is rather non-flexible, so that would be an interesting future research direction, to look for more flexible data transformation techniques. And then another interesting challenge, I think, is to regard the implicit sampling process that is sometimes performed during data acquisition, and to actually derive privacy guarantees from that already. So then I'm already at the end of my presentation. Thank you for your attention.
Thank you very much for your talk. Questions? Yes? Sorry.
I just have a question in the slide 10. I didn't see the value of epsilon that you had for your experiment. On the slide number 10, about the experimental result. I was just curious about the value of epsilon that you have for this number. The value of the parameter epsilon?
The value of the parameter epsilon, that was one. So we used the parameterization, which we found is suitable for our method, and saw how other compares with the same parameterization with ours.
Okay, thank you.
Any other question? Yes?
How does it scale? The number of complex rating?
How does it scale when the number of records in the input data set gets, very big?
Well, in terms of execution times, it was quite good, I have to say. All the experiments we have conducted terminated in less than 2 minutes, and the data sets we have used, they have this here US Census, time use survey, crash statistics, and health interviews. They have volumes ranging from 30,000 records to more than 1 million records. The number of attributes was about 10, so in that order of magnitude, the method performs quite well in terms of execution times.
Okay, let's thank our speaker again. talk will be given by Samir Bhatt and is about differentially private oblivious RAM. The floor is yours.
Hello. Thank you, Crustacia, for the introduction, and thank you, Griselda, for your laptop, without which I think this talk would have been difficult. Okay, so I'm excited to talk about our work on differentially private oblivious RAM. This is joint work with my advisor Pratik and Paul Cuff, who was a former professor at Princeton. So, okay, expected pointer doesn't work. Sorry, I was using the wrong one. Okay, so what is an oblivious RAM? So oblivious RAM is a mechanism for a user to access data privately, but from a private database. So as you can see in this graphic, a user wishes to request a record R from a database, and the user gets back the record R. But the obliviousness or the security property which we are aiming for here is the adversary, in this case the database, should not know what item was requested or what record was requested. ORAMs typically are deployed in two contexts. So the first one is in a client-server environment where the client could be a smartphone application. The server or the database in this case is the client's Dropbox or Google Drive account, and he wishes to retrieve a record from that. The other application scenario for ORAM is in a trusted execution environment such as SGX-based enclave. In that, the last level cache tries to access items from the DRAM, which is untrusted. So what's the problem with conventional oblivious RAM schemes? So if you look at how typical ORAM schemes work is you request a record, and what the ORAM scheme does is it makes a few fake requests on your behalf in some sense, and what this does is this increases the overhead of the scheme. Typical ORAM schemes incur logarithmic overhead for bandwidth and local storage, so that hinders their practical deployment. So the key insight which we introduce in this work is, can we improve performance by relaxing the privacy of these ORAMs? So thinking of statistically private ORAMs, we would like to have better performance at the cost of a privacy loss. But the important challenge here is, can we rigorously quantify such a privacy loss? And the second challenge is in terms of developing protocols which can actually take some of the privacy loss and translate them into benefits, performance benefits such as reducing the bandwidth or the local storage. Finally, we would like to achieve privacy proportional to the application resources. So for instance, if your application does not have enough bandwidth to run a full ORAM protocol, can you achieve maybe something like 50% privacy, but at the cost of a reduced overhead? So we solve the first challenge by using this notion of differential privacy. What we do is we introduce and formalize the concept of a differentially private ORAM. Now what this does is this gives a rigorous or formulation or mathematical framework to argue about statistically private ORAMs, which is ORAMs with reduced privacy. And then second, we introduce root ORAM, which is a family of statistically private ORAMs. In the second part of the talk, I will talk about root ORAM, which is this family of protocols. I'll give some theoretical and empirical results which talk about giving security guarantees about quantifying the privacy loss of these ORAMs, and also about the performance benefits we get on the other hand. And finally, I'll talk about an application of DP-ORAM which showcases the utility of that for the application of private information retrieval. So moving to differentially private ORAMs, this schematic sort of represents how a ORAM works. So on one hand, you have the program which gives the user an input access sequence. This input access sequence could be give me record 5, 10, and 20, for example. And then the ORAM protocol translates that into a series of requests to the untrusted memory, which in this case is server. The server is just going to act as a dumb mechanism which gives back whatever you request. So that's where the ORAM overhead is translating from A going to the output. And then the server gives back the requested records, and then the ORAM protocol gets back whatever was requested by the program. Now, what we have to note that ORAM mechanisms are statistical in nature, and so they are typically randomized, and so whatever input access sequence you have, you'll have a distribution on the output access sequence. So it's not one fixed output sequence, but it's a distribution. And then you have guarantees that this distribution should be just uniform, or it should look indistinguishable for any input sequence. In a differentially private ORAM, what we do is we consider this notion of neighboring access sequences. So you take in two input access sequences, A1 and A2, which differ in a single access. And then you study the effect of these differing access sequences on the output they produce. So more formally, if you look at this schematic, sorry, my slides go from one image to the next. That's how most of the talk is. But so if you look at this image, so the distribution of the output sequences on the input access sequence A1 is shown in red, and on A2 is shown in blue. And as you can see, the distributions are slightly different. And what we're really trying to capture is quantify the statistical closeness of these distributions, and that becomes your privacy metric, or that becomes your privacy loss. The smaller it is, the better privacy you have. So next I'll dive into the protocol construction. So this is the setup of root ORAM. On the server side, you have a number of binary trees. K is a parameter of the system, and for k equal to 1, you have two binary trees. Each binary tree, each node of the binary tree is called a bucket, and each one consists of multiple blocks, which is the smallest unit of data from the ORAM point of view. As you can see, the data items, at the client side, you have a mapping which is stored, where each data item is mapped to some leaf on the server side. Now let's take an example of what this mapping really means. So if we look at mapping, let's say data item 2 is mapped to leaf 1. What that means is we maintain this invariant throughout the protocol, that the data item 2, if it is mapped to leaf 1, it will be found on the path from the leaf 1 all the way to the root, somewhere along the blocks in that. So let's see how ORAM access works. So when you access, you're going to you're going to ask from the server the whole path from the root to the leaf, and you're guaranteed by the invariant that you'll find your data item in there. So that's the RAM part of it. So the next step is you update the mapping. So you randomly assign the block 2 to a new leaf. So in this case, it was mapped to leaf 2. Now the key insight here is about this update mapping. So if you use a uniform update mapping, then it leads to a conventional ORAM security. But if you use a non-uniform mapping, you get a differentially private ORAM. So in our case, the mapping which we look at is a non-uniform one, where the currently mapped subtree has a higher probability than any other subtree. And what this does is it lowers the average placements of the block when they are written back, which improves the performance. On the other side, it results in a privacy loss, because now data items don't move around as much. So let's just complete the protocol. So data item 2 was now mapped to leaf 2. So to maintain the invariant, we have to ensure that data item 2 is now placed somewhere along the path from leaf 2 all the way to the root. So what we do is we find the lowest common intersection of these two paths, which is, in this case, is marked by the arrow. And we try to place the block 2 in that location. So what we do is we take the item 2 from there and put it up in that demarked bucket. If you look at the whole protocol from the server's point of view, the server initial, so every time any data is written from the client to the server, it's encrypted with fresh randomness. So from the server's point of view, it sees a whole bunch of encrypted data blocks. And when it's read, it is going to give the client back one set of it. And when it gets back from client, it's going to get a new set of mapping. And so all it sees is the path to leaf 1 was accessed, and it was modified with something, but it doesn't see anything else. So I'll move on to the results. So first I'll showcase the theoretical results. So what we do is we show the above described protocol actually satisfies epsilon delta differential privacy for the following choice of epsilon and delta. This really shows that root ORAM is a differentially private ORAM for the following choice of parameters. The second result is an empirical one, where we showcase the performance improvements as a function of the security parameter. So on the x-axis, we have the security parameter. On the y, we have the improvement. And as you can see, the lower security you have, which is towards the right, the more performance improvement you get. The key takeaway from this would be DP-ORAM can be used to enhance at the cost of enhance the performance of a protocol at the cost of privacy. Finally, I'll talk about an application to private information retrieval. So PIR is a very closely linked primitive to ORAM. It's very similar to the setup in the sense a user wants to access data privately from a database, but except the difference is that the database is now public. So this could be a news website, it could be a US patent office where you wish to request a patent, or it could be, for example, PIR-TOR is a great example of a protocol which uses PIR to download TOR relays, TOR relay information. ORAM has been used previously to come up with PIR constructions. I've given two references down here. Typically how they work is you have a client who wishes to request a particular record R. What he does is he encrypts the client query to a trusted hardware on the server. The server now, the trusted hardware decrypts this query and then sends it to an ORAM protocol. The ORAM protocol then does the real working. It accesses the untrusted memory, it gets back the record, and then it gives it back to the trusted hardware, which then encrypts this response and gives it back to the client. So what we do here is, if this whole protocol becomes a PIR protocol, and if we replace the ORAM protocol with a differentially private ORAM, we showcase that this whole protocol becomes a differentially private PIR protocol, and the benefits of the differentially private ORAM protocol directly translate into benefits for a differentially private PIR protocol. So to see that, I have one quick slide on the comparison. So you can see here, the blue line is our differentially private based, differentially private ORAM based, differentially private PIR. And then these are state-of-the-art PIR protocols, DPPIR protocols. And as you can see, for any given value of the security parameter, if you consider the bandwidth which is required by the protocol, it's much, much lower. So DPORAMs can be used to give significant performance benefits for DPPIR. Finally, I'll conclude with just summarizing what I've talked about. So we first formalized the notion of a differentially private ORAM, which is the first one to talk about statistical ORAMs. We introduced a family of ORAM protocols and analyzed their security and performance. Finally, we showcased the utility of DP-ORAM mechanisms in general for the application of private information retrieval. I would like to give one major takeaway from this talk is it's possible to enhance the performance of a lot of protocols by relaxing privacy, which we are seeing more and more in literature with differentially private multi-party computation, differentially private anonymous communication, and this is just one such work in the line. Finally, our source code is available at our group GitHub page, which is down here. And with that, I thank you for your attention and would be happy to take questions.
Thank you very much. Questions? Oh, lots of questions. Okay.
Hey, thanks. So when you described your root ORAM, you said the change you make is that leaves in the same tree are more likely than in other trees.
Yes.
But how is it even possible to put a leaf in another tree because you're not writing back to anything in another
Yes,
tree?
that's a good question because I haven't given the details, like the full details of the protocol in there. So at the client side, you also have, let me see if I have a backup slide on that.
Backup slides.
Yeah. So at the client side, you have something called a stash, which is also the case if you have too many elements in one bucket, you don't have space, then things go into the stash, which stay locally. And so now you also want to prove that the stash does not grow beyond control, and that's also what we do in our paper.
Is the stash a single stash for all the trees, or
Yes.
do you keep a single one for all
it's the
the
same
trees?
one.
Okay,
Yeah.
thanks.
Hello. Great talk. Cool direction for ORAMs, by the way. Could you speak a bit more about the K parameter that you used? Because you said something about having to replicate the trees with the K parameter, but I didn't quite understand where that was going.
Yes. The K parameter can be used. I mean, there are multiple ways. Like it affects it's called the bandwidth parameter because it directly affects the bandwidth of your protocol, and it also affects the amount of local storage you require. So it's I'll defer you to the paper, but like if you look at it, like there are basically theoretical results, like how much if you change K, how much does the local stash change, and how much does your bandwidth get affected, and yeah, like actually. Yeah, I might have a backup slide, but yeah, we can take it offline if you want.
Hey, thanks for the great talk. I was wondering if you can build the PIR scheme from ORAM without using trusted hardware.
Let's see. Now you're putting me on spot, but let me see. At least not that I can think of. I mean, ORAM schemes are sort of if you see intrinsically, they require the client or like the user to have control or access of the database, because encryption is like one big part of it. If you don't have trusted hardware, I see it hard to because PIR, the database has to be public. And so if you don't have some kind of, not a trust assumption, but some kind of advantage you have in there, like I don't see a way of just taking a ORAM and like using it for a PIR. Does that answer the question? No? Somewhat.
So I had a question, which was,
Yes.
if I understood correctly, every ORAM access leaks a little bit of information. So that would mean that if you wanted to use an ORAM with some arbitrary program, maybe through a trusted execution environment, you have to think about how many RAM accesses it makes. Is that right?
Yes.
Okay.
So yeah, I think it has the same set of problems like differential privacy might have. You have to set a budget, you have to analyze how much each query requires, and then you have to set it appropriately so that you don't exceed the budget. We also have some results where, so this differentially private ORAMs are like, they have the same problem. So if your access sequence differ in too many elements, then it becomes, the privacy guarantees degrade, like not linearly, but there are results. And so what you have to do is either use this in, so this is not a silver bullet for like any kind of application, but if you look at specific applications, it might be good. So differentially private PIR is a great application because there the access sequence or like the secret just differs by one, because you have either you access this or that. And so that's one good use case, and then you can also mix it with like, so for DPPIR, we have these results on the lines of Toledo and Goldberg's work, where if you use an anonymous communication system, you can improve the privacy bounds a lot more. And so you can use much more, many more, sort of for the same privacy budget, you can do a lot more accesses. Yeah.
Any other question?
There's one back there.
Oh.
So I was just skimming through your paper, and for the evaluations that you have, you use z equals 5. But I know for PathORAM, for instance, if you use a smarter eviction strategy, like if you use reverse lexicographic eviction, you can make z as low as even 2. Would you still have an improvement over PathORAM if you were to squeeze that down to 2?
Yes. So I think these are constant performance improvements, and if you actually look at that, so that's Gentry's work on ORAMs, and so PathORAM itself can go as low as 4, but not below that experimentally, and Gentry's work can go as low as 2 with this deterministic eviction scheme. That's one of the future works which we have left, is to, because we can use the same techniques and apply to our work, and we can get benefits. Right now, it's going to be hard because we have a whole trade-off space, and so if you go, if you trade off your security for good enough performance, you can still beat those. But there'll definitely be points where they probably beat this scheme, and yeah, so that would be my answer.
Okay, thank you.
Okay, I think we should stop here.
Thank you.
Thank you very much. So there is a short break, and we'll resume in 15 minutes.
Florentin, and I'm going to talk about. So hi everyone. I'm going to talk about unwanted consequences of flexibility in onion routing protocols. So this is joint work with my thesis advisor Olivier Pereira, and it has been done at the UCL Crypto Group in Belgium. So let's start with an overview of the most known onion routing system. So these big colorful figures, I'm going to attract the attention of two concepts with this figure. So the first one is the concept of guard discovery attack. So on the top you can see a client connecting to the Tor network and using a big circuit composed of in fact 6 relays. So there's in fact two circuits into it, joined by the rendezvous. And by the path selection design, you are guaranteed to always have the same entry point at the other end. So the onion service is always going to have the same entry nodes. And so it's why that a guard discovery is a serious problem in this protocol, because if you find the identity of that guard, you are very close to de-anonymize the onion service itself. So this is the first concept. And the second concept is what you can read in titles, dropping on the edge. The edge is where everything interesting happens in this work. So it's most of the time the endpoints of TORCircuit, but it's not always that. So for simplicity reasons, let's consider that it's always the endpoints of TORCircuits. We know that the internet is built from various protocols, and some time ago, in fact a long time ago, people gathered and put some guidelines about how to design protocols that have been found useful when they designed the protocol that we use today in our daily lives. And in fact, you have this robustness principle, which is one among them. And this principle tells you that you have to be tolerant with what you receive from the others. And one of the contributions of this work is to show that this principle can lead to strong attacks. And various protocols use this principle. Even the Tor routing protocol uses it. So in the Tor routing protocol, the robustness principle is used with forward compatibility. So what is it? It allows compliance with future versions of the protocols. So if you look into this piece of code, this function is always executed in endpoints of TORCircuits when the nodes receive a cell. And basically, like in any network protocol, you have header, you have a payload, and this function is just going through all the possibilities and to know what to do with that particular cell or packet. And if it does not know what to do because the packet is irrelevant or other, it's just going to ignore it for forward compatibility reasons. And for the remaining of this talk, my job is to convince you that this behavior that seems inoffensive is, in fact, has some security concerns. So I'm going to show you this with two attacks, guard discovery attacks and traffic confirmation attacks. So let's start with the guard discovery attack. So it combines three components. So the first one is a path selection trick. So this is what you can see on the picture. The idea is to build many parallel circuits towards the same onion address. And by design of the path selection, you are going to obtain this. So just to remind, these attacks, you don't need to run any relay inside the network to discover the identity of the guards. You just need to have modified your clients. And so the second component of this attack is to use the forward compatibility to send as many cells as you want, depending on the numbers of parallel circuits you have, that are going to be ignored by the onion service by the other side. And doing this, you are going to create what's a perturbation, and this perturbation you can see it with a side channel. And the side channel that we use to recognize the guard is in fact the public measurements of relays. So each relay reports each day measurements about the bandwidth that they have sent and received. And we can use this public information to try to look for a bump when we apply this attack. So you can see here on the right, it's a graph that has been plotted by a public service showing the result of an attack over my own relay in front of a DUMI onion service. So we know that it's possible to do. The question that we want to answer is what's the success rate of such an attack in the wild? So to answer that question, we make some assumptions. So we make some assumptions about, for example, the fact that there is a graceful behavior of the relay, meaning that it's not going to be offline during the attack. And with those assumptions, we can in fact use the history of the network to evaluate the attack. So the history, all the past history of the network is registered, and you can exploit this information to simulate it. We are going to distinguish several situations. So in this first situation, you have a bottleneck on the onion service, meaning that the guard relay is not able to send as much bandwidth as it would like, so it's going to buffer the extending cells into its memory until the memory is full. When the memory is full, Tor call, so the guard relay is going to call an algorithm to kill the circuits and recover the memory. But this algorithm allows trivial discovery attacks because it's going to desynchronize counters in the public history. We have a read counters and a write counters, and if you call many times the out-of-memory algorithm, you have this desynchronization that happens. And we can see in this figure over a private network which of the relay was actually the guard relay of the onion services. So, but this is a bug, it can be fixed, this one. So we are going to consider that this bug is fixed for the rest of the analysis. And here in this situation, we consider that the onion service, the bottleneck is on the guard relay. So when the bottleneck is on the guard relay, what you can do is consider that the guard is going to saturate. So you can build a classifier and try to recognize into the history for what parameters of the attack you are going to have possible candidates among the guards. So if you look at the right figure, this gives you the number of possible candidates for different parameters. And let's look at the bottom lines. So the bottom lines is an attack duration of one complete day. Sorry. And for a threshold of 1.2, the threshold is the size of the bump, if you want. You are going to have something like 20 possible candidates. And the more you increase the threshold, the less candidates you have. But the more you increase the threshold, also the less likely you are going to find the correct guards inside your candidates. So This is a trade-off. And to know exactly what's the probability to miss the guard relay, the correct guard relay, we need to look into the spare resource of each guard, because the bump that you're going to see in the history depends on the spare resource of the guard. So, but hopefully for the attack, a lot of guards have spare resource. So you can see this on the left graph, which gives you, for example, that 80% of guards relay are used at half of their bandwidth. So knowing that information and knowing also the distributions of probability for the selection of guard, we can compute the probability of false negative for a given threshold. So the idea is to keep the threshold low, to not miss the guard, but you're going to have many candidates. And what you can do is to simply repeat the attack and take the intersection set until only one relay remains. And it's going fast enough. So also what we can do if we do the assumption that the counter exploit is fixed is to consider various bandwidths for the onion services. And the lower bandwidth of the onion services, the more difficult the attack to succeed, because the classifier is less likely to observe the bump into the history. And at the end, in a way, for a few megabytes onion service, you have a high success rate to retrieve only one and correct guard in a few days. So hopefully the Tor project did a great job to react to this problem and also to other guard discovery attacks. So there is no Vanguard that is available online, which is a set of mitigation for that kind of problems and others too. And you can check out. So the second attack that exploits forward compatibility is a traffic confirmation attack, but with interesting properties. So the interesting properties is the fact that it does not need any byte. The victim does not need to transfer any byte to be correlated over its circuit. So, and the application level traffic does not influence the success rate of this attack. And use also forward compatibility and a side channel. And it has been tested in Shadow with high success rate. And yeah, it can be applied in many different scenarios. So here's a scenario of the attack. So let's assume that you fetch a page on Tor browser. So this is what's going to happen. So you have first your onion proxy that sends the information for the exit nodes to connect. And this information is sent through the begin cell here. So once the exit relay, the correlating exit relay gets the information, it locks the IP of the destination websites and send back cells that are going to be ignored by the onion proxy in accordance with the flexibility design of the protocol. And so along the path, the guard relay will be able to, with a timing analysis, to spot the difference with a scenario when you don't have such mark. Because if you look careful at the exit connection, here in fact, there is a TCP handshake. Then once the TCP handshake is finished, you have a connected cell that is fired back to the client to say to the client, I'm connected. And this connected cells, because of the transport layer, is always guaranteed to be alone in the circuits if we don't have congestion of the middle nodes. And the drop mark attack is simply breaking this guarantee. And it works pretty well on simulations. So to conclude this talk, I just maybe want to try to start a discussion about forward compatibility. So I've heard about from one developers of Tor that they consider to remove it. I'm not sure that's a good idea because apart from the good properties that forward compatibility gives, I'm not sure it can solve the problem. So the idea is if you remove forward compatibility, let's take the example of the previous attacks, instead of silently ignoring the packets, you are going to kill the circuits. But since the robustness principles is everywhere in every protocols, you can probably craft cells that are going to be ignored at the application level but not at the onion proxy. So it's going to be total valid from Tor layer, but not the upper layer. So I'm not sure it can really solve the problem to remove forward compatibility at the Tor layer. That's it for this talk. Thanks.
Okay, any questions?
Thanks. I mean, just like what you said, if you go back to the flow diagram, like the colluding exit could send pretty much any cell type to the other end and make a pattern that will be visible, right? So I agree. It's not the backwards compatibility that's the problem here. It's
not. Yeah, but the problem is without forward compatibility, you can notice that it happens. So you can react to it. You can say, oh, this exit node is maybe a malicious node, and you can
maybe, but you could the colluding exit could send the connected cell early, and then send any pattern of traffic it likes.
Yeah.
Right. I'm not seeing why it's the forward compatibility's fault.
If I may, the colluding exit could, for example, if you're downloading something of any appreciable size, introduce, describe the content in Morse code on the wire, and the client would be similarly silent even though the exit is introducing no traffic.
Yeah, but it uses the application level traffic of the user to do that. So there is many connections on the Tor network that does not have many traffic, and those connections with these techniques you're not able to really do traffic confirmation on them. This technique does not need any traffic on the application layer to succeed. That's the main difference with what you said.
I think I missed some forest for the trees or vice versa or something, but the exit knows the destination. Yeah. And so what is it that he's even giving away that he can't just communicate? I mean, if he knows the destination and he's colluding somebody on the other end, then why isn't that the whole game?
Not the other end, it's on the path, so you want to collude with the guard relay. Yeah, because you want to do the end-to-end correlations attack. So the guard relay is going to log the IP address of the onion proxy when it sees the drop mark. If it's a colluding guard, if it's not a colluding guard, it's just it just applied protocol and nothing's wrong.
Any more questions? No? Okay, well, thanks. Just in time.
Just in time. So there's one other interesting thing from this paper that I wanted other people to think about. When the client sends a destroy cell to the guard saying, I'm done with this circuit, please tear it down, the client thinks, okay, the circuit's gone. It can never be used to attack me anymore. But if the guard is malicious, the guard can say, okay, I've gotten rid of the circuit, it's gone, but the guard can leave the circuit between the guard and the middle and the exit up, and the exit and guard can send stuff back and forth. There are some constraints on this. As long as they like and the client doesn't even know that it is still happening, this worries me. I don't know how to turn it into a bad attack, but it worries me.
Yeah, any more questions? No? Okay, thank you.
I disconnected this, so I want Let me just connect this. Okay. Okay, thank you. Hi all, my name is Mohsen. I'm from University of Texas. Okay. Hi all, my name is Mohsen. I'm from University of Texas at Arlington. Our work is about forming guard sets in Tor using autonomous system relationships. This is a joint work with Armand Barton from University of Texas, Arlington, and Professor Matthew Wright from Rochester Institute of Technology. So, as you all know, Tor is a privacy-enhancing technology that provides online anonymity for internet users. In Tor, traffic goes through 3 randomly selected relays, and an encrypted tunnel is created through these 3 randomly selected relays that we call this encrypted tunnel as a circuit. If the first node and the last node in the circuit, they are malicious and they are controlled by the same adversary, the adversary can do traffic correlation and de-anonymize the user. So the Tor strategy here is to use guard lists. Instead of picking a new guard for each circuit, we pick a small set of guards and we use them for building circuit. Before 2015, the size of the guard list was 3, and after 2015, the size dropped to 1 guard. Using guard lists has some drawbacks. For example, one of them is guard fingerprinting. So because the number of guards in the network, they are large, and the clients, they pick their own guard list, each client may have a unique set of guard lists. As you see in this image figure, client A, B, C, they have different guard lists. So this guard list can be a fingerprint for the attack for the client, and there are some attacks that they can identify relays on the circuit. If the attacker can identify the guard on the circuit, the attacker can de-anonymize the user. Even if the attacker is not able to detect guard on the circuit, we still prefer huge anonymity set, a large number of clients using the same set of guard lists. Because through some attacks like a statistical disclosure attack, the long-term behavior can de-anonymize the user. So one of the solutions here is to using guard sets. Guard sets, they are like guard lists, but they are non-overlapping group of guard. So we break the list of guards into the few sets, and each client pick one of them. So as you see in this figure, we break the list of guards into the 2 sets, and each of them has 2 clients. It means that the anonymity set size is 2. If the attacker can identify the guard on the circuit, the attacker cannot detect the exact user. So the question is how to form the guard set and how to attach the client to the guard sets. The first attempt was made by Haynes and Denises in 2015, and we called this design as a bandwidth design. Their idea was to use guards bandwidth in forming guard sets. So in their design, as you see in the figure, they first sort the guards into the network, and then they build the guard sets in a way that each guard set, they should have at least 40 and maximum 80 megabyte bandwidth. So the first relay has 90 megabyte bandwidth, so it's broken into 2 equally sized guard sets. And the second relay has 65, is less than 80 and more than 40, it goes to a separate cell. And the third and the fourth guard relays, they go, their total bandwidth is 70, and they go to another set. So, and they build all the guard sets in this way. Even if the guard set's bandwidth drops to below 20 megabyte, they repair the guard set. In the repair phase, they add guard relay to the broken set in a way that it has a similar bandwidth. Oh, sorry. Jump out, sorry. So in the repair phase, if the total guard bandwidth it drops to less than 20, there adds guards relay that they have similar bandwidth to guards relay in the set. For example, if we consider this guard set that it has two guards relay, 20 and 30 megabyte bandwidth, they add, and if the total guards bandwidth drops to less than 20, it for example is 50, the attacker can tune his bandwidth to around 25, which is between 20 and 30, and gets into that set and compromise that set. We use this vulnerability and attack this system in two different attack scenarios, low bandwidth adversary and high bandwidth adversary. In the low bandwidth adversary, the attacker leaves the guard set even if the attacker provides 90% of the total guard bandwidth. And in the high bandwidth adversary, the attacker stays in the set forever, even if all the other guards relay are gone in that set. So in these figures, the blue line shows the fraction of bandwidth controlled by the attacker, and the red line shows the fraction of compromised guard set. In the low bandwidth adversary, the attacker that controls 1 or 2% of the bandwidth, guard bandwidth, the attacker can compromise around 40% of all the total guard sets. And in the high bandwidth adversary, if the attacker controls 30 to 40% of the total guard bandwidth, the attacker can compromise almost all the guard sets. In our design, we wanted to stop the attacker from going from one set to another set, and we wanted to tie the attacker to his network. In order to understand our method, we need a little bit background about autonomous systems. Autonomous systems, they are single ISP or multiple ISPs that they are controlled by the single authority, for example, a government or a university or an organization. The relationship between ASs are governed by economic and political constraints. For example, if we have a client, he wants to visit a website, if the client is AS1 and he wants to visit a website in AS3, the traffic from a client and to the web server goes from AS1, AS2, and AS3. We consider AS2 as the provider, which provides transit between AS1 and AS3, and we consider the AS1 and AS3 as a customer. We have a concept in AS relationship that we call it customer cone. In customer cone, we consider that all the customers that they are under the same provider as a customer cone of that provider. So this figure shows the customer cone of AS1. As you see, a customer cone can be nested, and also they can have overlap because some ASs, they have multiple providers. So in our design that we call it AS design, we use guard network to form the guard sets. So the advantage of this is that we can find the attacker to his network, and we stop the attacker from running multiple relay from the same network and getting to different guard sets. We define a hierarchy in our design. At the top of our hierarchy, we have root sets, and we break each root set into few branch sets. And further, we break each branch set into few guard sets. Root sets, they are big customer cones that they have huge amount of bandwidth and a large number of guard relays. And we break each root set into few branch sets. Branch sets, actually, they are a small customer cone into the root set that they have at least 40 megabyte bandwidth. So this figure shows the root set, and customer cone 4, 5, and 6, and 7, they are a small customer cone that we consider them as a branch set. We further break each branch set into few guard sets. Our policy in forming guard sets is that each guard set, they should have at a minimum 40 megabyte bandwidth, and also they should contain minimum number of guard AS in the guard set. So if you see in this figure, this is a branch set, and it has 3 guard AS, autonomous systems. We add 1 guard at a time to the guard AS to reach to the bandwidth 40 megabytes. So these 3, they have 42 megabyte bandwidth, and they go to a separate guard set. And we build the same, it's the same way other guard sets to use all the guards relay. So the way that we attach guard sets to the client is that the client first picks randomly a root set among all the root sets. The selection is not completely random, is in the favor of high bandwidth root set, and then in that root set, the clients pick randomly a branch set. Again, the selection here is in the favor of high bandwidth branch set. And further, the client pick a randomly guard set among all the guard sets in the selected branch set. So in our design, we define 3 attack scenarios. In the first attack scenario, we can that we call it low resource adversary. We consider that we have a single malicious guard relay in the network, and we wanted to measure how much this single relay can compromise a client. And in the second attack scenario, that we call it high resource centralized adversary, we assume that the attacker controls 5% of total guard bandwidth, and the attacker runs all of his guard relay from a single AS. And the last one, that we call it botnet adversary, we consider that the attacker controls 5% of total guard bandwidth, and the attacker runs all of his guard relays from different AS, from different network. So in these figures, x-axis shows the time, year 2015, and y-axis shows the fraction of compromised client. And color band shows the 25th and 75th percentile. And sorry, something wrong with my. And the line shows the median value of compromised fraction of compromised client. And we compare the result with vanilla Tor and previous design, a bandwidth design, and the green one shows our result. If you see in all of the attack scenarios, our result works pretty better than previous design, bandwidth design. And even if in the high resource centralized adversary, our result is better than vanilla Tor, unmodified Tor. The reason is that in that attack scenario, the attacker add all of its guard relay from the single IS, and all of them, they go to a single guard set or very few guard sets. And also, our result, they are pretty stable. And over time, the fraction of compromise rate in our design doesn't change too much compared to other attacks, compared to the other designs. And also, we have a jump into the compromise, the fraction of compromise relay in August 2015 in bandwidth design. The reason is that in August 2015, for a few days, we had a drop in total guard bandwidth. This total guard drop in the bandwidth caused a huge churn into the guard sets created by bandwidth design. So it enabled the attacker to get into the lots of sets. So, but our results, they are not sensitive to the bandwidth fluctuation. This figure shows the left one. The left figure shows the anonymity set size, the CDF of anonymity set size that we compared with vanilla Tor, AS design, and bandwidth design. AS design and bandwidth design, they have almost the same anonymity set size in terms of median, and they are far away from the vanilla Tor. And the right-hand figure shows the median of guard sets bandwidth. Our guard sets have a lower bandwidth compared to the bandwidth design. The reason is that in the bandwidth design, they only use bandwidth to form the guard sets. And in conclusion, we used guards network to form the guard sets, and it's enabled us to confine the attacker to his guard, to his network, and stop it from going from one set to another set. And our result actually showed that our guard sets, they are pretty stable and they don't change. The attacker actually cannot compromise too much client over time, and our guard set wasn't sensitive to the bandwidth fluctuation too much compared to the previous works. And thank you very much, and I'm ready to take the questions.
Okay, questions? So on, I think, slide 20, when you say you select the branch sets that are higher bandwidth with
Yes.
more likelihood, is that just directly proportional? Like, do you just select it with weight equal to their bandwidth?
We just select them based on the bandwidth, so we weighted, but that we computed based on the bandwidth fraction of the bandwidth that the root set has.
Yeah, but what is that based on? Is it
So the
just
sum
directly?
of all we compute the sum of all the bandwidths. For each root set, we compute the total bandwidth divided by the total.
Okay, so just directly proportional. And I had another question. Go right to the end again.
Here.
No, not that one. Great. Oh, right. So who computes these guard sets?
Authorities.
The
Internet for-
authorities. So
yeah.
the authorities need to know the AS topology,
Yes.
or at least guess at it.
So, yeah.
But only
So
the 9 of them.
Yeah, we use, for example, Kydia dataset to compute to find the AS relationship and find the customer cones.
Right. And I guess the 9.
What?
The 9 authorities will have to agree and come to consensus on this.
Yes.
What happens if they disagree? Did you model that at all?
No, we just we
Like
we use just one source. We use one source to compute the guard sets and to compute the internet backbone, actually the customer codes. And we didn't use, for example, all of them they should come to one consensus.
Right.
Yeah.
Okay, thanks.
Any other questions?
A question from the internet. Would you agree that your design introduces a new attack vector, a malicious AS to IP mapping source? Or what IP to AS mapping source would your design use? Yeah, I'm also a bit confused about the question.
Oh, okay. So how do we build that customer code? So we use a Kydia dataset. So we use the Kydia dataset to find AS relationships, and we use recursive algorithm to find the customer cones. So yeah, the attacker, for example, the one in AS can be malicious, and the attacker can, for example, put its relay into the one specific guard set and target that specific client that using that guard set. But the attacker cannot detect, for example, which guard set it will go, because we have the attacker put his guard set into the single AS, but it doesn't know which guard set it can compromise, because it's within the hierarchy. And also the effect of the attack will be very limited, because if we have a hierarchy, an attacker can, if the attacker compromised a single AS, it can compromise a various, not all the clients, just a specific set of clients that they are using that guard set or branch set or root set, not all of the clients.
Yeah, I was wondering if you could talk more about how you evolve these sets over time as relays drop out of the network. How do you keep enough guards in your set, or prevent clients from switching between sets?
So at the beginning, each for example, we consider that if the bandwidth goes, for example, below 20, we need to repair that guard set. Even for example, we have some newly joined guards in that guard set in that areas. We add them to the broken set. If, for example, we don't have it, we attach it to another guard set that we have. For example, in one single AS, we have one small set that is broken, and we have one set that is not broken. So we attach it to the other one to have a single guard.
So then your evaluations were over time. Was that evaluation doing this repairing?
Yes,
and
I didn't
pasting
explain
thing?
the updating phase because of the time. So we have, for example, at the beginning of each round, we first repair the broken set, and then we build another set if we have enough bandwidth. Yeah,
Any other questions?
I noticed you didn't show a performance evaluation. I was wondering if you anticipate this to affect performance in any way.
Yeah, we actually we evaluated in shadow, so we didn't see any significant change into the performance of the design. We spent a lot Tor and also bandwidth design. They have almost the same amount of performance. Then this information they are into the paper, and I didn't add it to the slides.
Any other questions? Okay, thank you.
Ryan, and I am here to talk to you today about my paper, Tempest, Temporal Dynamics in Anonymity Systems, which I worked on with my friends Ishin Sun, Aaron Johnson, Meng Cheng, and Pratik Mittal at both the US Naval Research Lab and at Princeton. So as the title of this work suggests, we're looking at how time can affect anonymous communication systems, and in particular low latency anonymous communication systems like Tor. So over the past decade, there has been a lot of development in low latency anonymous communication systems. There have been lots of works that appeared at top venues, and we found that a lot of these works ignore time. And kind of as an example of this, you might see a new protocol appear, and in the security evaluation, they will simulate a client which makes a connection through a static network, a single connection. They will evaluate the anonymity of this connection, make some conclusion about security, and move on. But this isn't how systems work today. People don't make a single connection through Tor and then delete Tor off their laptop. So in our work, we looked at three real-world phenomena, which are time-based. We call them temporal dynamics. And these dynamics are often ignored and can impact system security. So the first is that clients can move over time. This is pretty simple. People use Tor on laptops and on cell phones. And we call this dynamic client mobility. Also, users are inclined to use these systems for long periods of time and may make many connections to these systems. And the third dynamic we identified is called routing changes, and it's just the observation that the internet path between any two hosts can change. So these are the three dynamics that we looked at, and we looked at how they interacted with a variety of systems. So in the top half of this table here, I have Tor and recent modifications to Tor, which were proposed to improve its security. And in the bottom half of this table, I have newer protocols which operate at the network layer as opposed to the application layer where Tor operates. And there are some ways that these dynamics, some limited prior work which analyze how these dynamics interact with these systems, but for the most part we found the space was relatively unexplored. So in our work, we identified a lot of attacks on these systems which leverage these dynamics. And this table is kind of packed, but what I want you to pick out is that for every row, every one of these systems is affected by at least one of these dynamics, and in every column, each one of these dynamics can be leveraged into an attack across both Tor-like protocols and these newer network layer protocols. So we think this is a serious issue and one that we should address. So to give you an example, there's too many systems to cover in this talk, but I'll give you an example of two of the dynamics and how they affect two of the systems. So I'm going to look at client mobility and how it affects Tor, and user behavior and how it affects a Tor-like protocol called DNASA. To give you a very brief background on Tor, clients make a connection through three Tor relays, a guard, middle, and exit. For each new circuit that a client builds, he will choose a new middle and exit relay, but a client will use a single guard for a long period of time, a couple months, although this rate might be accelerated if, say, the guard goes offline, the client may be forced to choose a new guard. And the other thing you need to know is that relays are selected with probability proportional to their bandwidth. So, I'll show you an example of this in a minute. Okay, so let's look at the first dynamic and see how it interacts with Tor. And let's start with me as an example. In my travel to PETS this year, I was using Tor. And the day of my flight, I started out and I connected from home, and I ran a trace route to see who could see the traffic to my Tor guard. And there were three networks: Verizon, a transit network called Tata, and then finally the AS of my guard, which was LeaseWeb. But then I started moving around. I connected to a coffee shop when I got coffee before my flight, and that allowed two more networks to see my client guard traffic. And this pattern continued. I connected from my phone, that added AT&T, etc. And by the time that I was done, and I had traveled to PETS, an additional 7 ASs saw my client guard traffic, which was a 3 times increase over when I was just connecting at home. And I had connected to Tor from 6 different networks. So my claim is that this is a bad thing, this weakens security. And in particular, I'm worried about a passive adversary here who controls a single AS. This is a very common adversary model in Tor research. And the adversary's goal here is to observe client guard traffic. He would do this, for instance, if he's interested in running traffic correlation attacks or website fingerprinting attacks. This is the place where he wants to be. Okay, so the questions we wanted to answer in this analysis were, how mobile can some clients be, and does this mobility weaken system security? So we really wanted a data set of how Tor users move around. But there is no such data set. If you have one, you're kind of in big trouble. You should probably leave. So we did find data sets about how people moved. And in particular, we looked at two publicly available data sets about how users moved in these social networks, Foursquare and Gowalla. So each of these data sets contained location traces for a few 100,000 users over a period of about 1.5 years. And we had check-in histories for these users. So we knew at certain times they checked into certain countries. We knew which countries they visited, more or less. And so we looked at, in both data sets, how many distinct countries did these users visit. So the top half of the table shows users with distinct country movements, like how many there were. And in both cases, we found that in about 25% of users had at least visited 2 distinct countries, and there were travelers who visited more countries than that. And on the bottom half of the table shows the first quartile of how fast the users moved around. So in the 2 column and the Q1 days, that says that for 25% of the Gowalla users, they visited 2 countries in 7 days or less. And so we find that some of the users in our data set, not a small fraction, both were willing to travel to many countries and traveled very quickly. In less than a few months, some people visited more than 6 or 7 countries. So we made a conservative assumption then and said, we don't really know where these users are connecting from, but let's just assume that they connect from the top Tor client ASs from each country. We used an existing data set, the Joen data set, to determine which Tor ASs were popular. And then we looked at the probability that one of the largest 50 ASs on the internet can compromise the client guard link. Okay, so let's look at some data then. So how to read this graph. The y-axis shows the probability that if I'm the average top 50 AS in the internet, one of the average largest 50 AS in the internet, the probability that I compromise the median user are the points in the graph, and then the shaded region is the distribution over all users. It shows the range over all users. So the bottom left point at 1 and then 0.3 says that if I'm the average top 50 AS in the internet, and the user didn't move around, they stayed in one country for the entire time which we had data, then the probability that it compromised them is about 3%. As they start moving, that probability increases. Once they have visited 3 distinct countries, the probability doubles in both of our data sets. And for some of the most, for the users who travel the most, we found that the probability can increase 9 to 10 times. So the risk for these users would be underestimated by almost an order of magnitude if you didn't consider mobility. Okay, so that is client mobility and how it can interact with Tor. What I just want you to take away is that many clients are mobile today, and that mobility can reduce system security. To look at maybe a more involved example of a dynamic, we can look at user behavior and how it affects a system called DNASA. So DNASA has an algorithm called gselect, and the gselect algorithm is pretty simple. It just says, don't select guards where one of 2 ASs is on the client guard link. So that is AS1299, which is Telia network, and AS3356, which is level 3. So how this looks like then is if I'm a client and I have 3 guards to choose from, maybe they have 3 different probabilities. The first 2 have probability 1/4, and the third has probability 1/2. If AS1299 is on the client guard link, I will reweight the relays accordingly so that I won't choose G1 anymore, but I'll choose G2 and G3 with the same relative probabilities. But this leaks some information. So if there is a second client who has a different set of links to these guards, the observation here is that G3 is chosen by these two clients with differing probabilities. The client in AS44 chooses G3 with probability 2/3, whereas the client in AS88 is choosing G3 with probability 1. And what this means is, if I'm a middle relay and I see G3 on my circuit, well, I don't know where the client's coming from because that's a general protection that Tor provides, but I have gained a little information. If I condition on G3, I now know that it's a little more likely that the client is coming from AS88 than it is that the client is coming from AS44. But that observation itself is not novel. Our contribution is that this leak can get very bad over time. So in particular, if the adversary is able to observe many guards for a client, then the adversary can effectively learn the client's location. So how can an adversary learn many guards for a user? Well, we're going to consider an adversary who runs a destination and some relays. We can consider like a cloud service provider like OVH to be such an adversary. And he's going to be a passive adversary, and his goal is going to be to learn the client AS. Okay, so to see what this looks like, let's consider a destination which is like a pseudonymous forum where a user can post under a pseudonym. And the user is going to use Tor to protect his identity, his real identity, but again, the adversary is going to run some middle relays and also is running the destination as like the cloud service provider. So on day one, the client connects to the destination through Tor, maybe makes a post. On day two, he does so again, but chooses the adversarial middle relay in this case. He runs a traffic correlation attack, and using his observation of the circuit, he now learns that the client is using G1, this pseudonymous client. On day three, his guard goes down. He chooses a different guard, makes a connection through the exit. On day four, he chooses the adversarial middle relay again, and now has learned, again using traffic correlation, that the client is using G3. Okay, so two things to note at this point. This is one guard discovery attack. This is like the predecessor attack, but there are others. There's the throughput fingerprinting attack. Florentine just presented a guard discovery attack. And the adversary can use any of these. And also the adversary can get clever about how he's linking client connections. For example, he could be looking at an SSH server and sees that only one client ever connects at 5 p.m. every day. And that might be the way that he links together these connections. So once he's made these observations, he can compute a posterior distribution over where he thinks that the client is coming from. So to evaluate this attack, we looked at all 60, or we gave the adversary no prior information about where the client's coming from. We just assumed that the client is coming from one of 60,000 ASs on the internet. We looked for some leaky client ASs using some heuristics. We identified 10 of them. And then we simulated a client making connections out of these ASs for up to 6 guard selections. We repeated this procedure 100 times for each client AS. And then we looked at the average posterior entropy of the adversary's location distribution over client locations. So this is the plot of that. And in the top left, the adversary starts out with like 15.5 bits of entropy. But as time goes on, entropy decreases dramatically. So you see that after one guard observation, the client loses some bits of entropy. But after two observed guards, the adversary can effectively learn the client's location in most of the ASs we looked at, which is really bad. So what I want you to take away is that these small leaks can become significant over time, and that it's also important to consider the worst case here, because some of these clients might be in these ASs and they might really need the protection that Tor provides. And so we want to not have any of these worst case ASs where you might not know if you're in one. And we don't want to erode trust in the network by having these degenerate cases. So in conclusion, there are a lot of systems we looked at in this paper. I presented 2 of the attacks and 2 of the systems, but I hope that if your system is up here, you take a look at what we did. And we don't think that these systems are totally broken. So I think there's promising research in addressing these dynamics explicitly. We also want to motivate researchers to consider the long-lived adversary, one who is interested in aggregating data about users and de-anonymizing users over time. And also, we think that the research community in general could use better tools in both evaluating these systems over time and also in formalizing the security that these systems can provide over time. Okay, so that's my talk. Aaron and Pratik are both here, and if you're interested in this kind of thing, you should also talk to them. Thank you.
Questions? Hey, thanks for your talk. Great. There is a model that has driven Tor security since years, which is that being compromised once is as bad as being always compromised. And do you think that this model makes also sense for people that travels a lot?
Wait, can you repeat the first part of your question?
So there is a model that that has driven Tor research security, and this model says that being compromised only once is as bad as being always compromised. And my question is, do you think that this model makes sense for people that travel a lot?
So, yeah, I think it depends on the adversary that you're considering. And it also depends on user behavior. So if my behavior is very repeated, then like being de-anonymized once, like being de-anonymized down to my pseudonym is as bad as being de-anonymized forever, right? Because once someone can associate me with my pseudonym, then I lose. But again, it depends on what you're doing. I think it really depends on like the user model and the adversary model that you have.
So nice work. In the part about attacking Tor, you were using an average of the compromise rates over top 50 ASs. And so in our work in NASA, of course, we found that, well, really, it's just the top few ASs, by some definition of top, are responsible for like a huge amount of the potential compromises in Tor.
Sure. So
did like this average of the top 50 is actually quite a conservative metric, I would guess. Did you find that in the data?
Yeah, I think we looked at top 50 because we didn't want to make assumptions about the exit destination link, which I think is where the suspect ASs in DNASA came from, right? Those are the most likely to be on both sides of the circuit.
Both sides of the circuit, yeah.
But we didn't want to make any assumptions about what the users were doing. So we just kind of assumed that the top 50 ASs were the ones that were probably most likely on the other side of the link, but we didn't want to make any assumptions about like if they were visiting Alexa sites or not, anything like that.
But just in terms of, I mean, when you look at the data that you had, like you probably had, here's all 50 of them, did you find that some were like really, really responsible for a lot of compromises, or?
I don't know if we looked at probability rates for individual ASs, more than just a handful, and I think they were similar. The largest ones were somewhat similar to the ones that we're presenting.
Okay.
Hi, thanks for the talk. On one of the slides showing the second example, you spoke about leaky locations.
Yes.
What does this mean? Or could you give an example about this?
Yeah, so the ASs that we finally evaluated, the leaky ones are the ones which lose entropy over time very quickly. So these are the leaky ASs. We found 10 of them. We showed 4 of them here. The other 6 were very similar to these. But those were the ones, we just used heuristics to search through the space to find ones that leaked information very quickly.
Last question, anyone? Ian?
Could you identify like what caused them to be especially leaky? Are they highly connected or poorly connected?
Yeah, so I think many of these are highly connected with Thalia, and so most of their traffic went through Thalia, but there were a few guards which they didn't route. Like they only had very few guards to choose from. So when they chose those guards, it was very they chose them with much higher probability than any of the other ASs. So when they chose those guards repeatedly, then it was very obvious that those guard selections corresponded to clients in those ASs.
Right.
Okay, thank you, speaker again.
Thanks.
Okay, so next session is on tracking in half an hour. Is Narceo here? Session chair for next one? Okay. No? Okay, please try to find your session chair. See you in half an hour.
Okay. Hello, everyone. So let's start with the final session of for today, and it's going to be about the creepiness of mobile tracking in the era of GDPR. And the first talk will be by Hassan from Data61, who will be presenting touching youth and your trap, quantifying the uniqueness of touch gestures for tracking.
All right, hello. So I'm going to talk about touch and you are trapped. The C and K are silent. So it's about how the way we use our touchscreen devices could be used for tracking. So it's a joint work with Rahat, Ben, who are not here, myself, and Dali. So I'll begin with a typical scary stat slide. So I think for this audience, it's not a new news that mobile apps collect a lot of information. Some of it is related to the device we use. Some of it is related to more personal information, like, for instance, location. This is from a study from Zscaler, which is an information security company. It basically shows that many of the apps from iOS and Android leak personal information. By leakage here, I mean that when these apps send information to the server, these are sent in the clear text. So some of this information is meta information, like the device ID. Some of it is location information. Some of it's even more personal, like email addresses, and also contact information. So these details could be used to track users. So it could be used for, so tracking could be done using the device configuration, could be done with how you have personally set up your phone, and could also be done through user behavior. So, which is the focus of the talk today. So in particular, I'm going to talk about touch tracking. So what is touch tracking? We define it as tracking a user continuously and in the background without the knowledge of the user, while the user uses its phone or other device in a normal way. And we consider it as a new privacy threat, and particularly dangerous because it could actually identify the actual physical user behind the device. So if the same user is using multiple devices, it could be used to track that user, which is slightly different from, say, browser-based tracking, where in fact you're tracking the browser used by in a particular device. So not all of the use cases of touch tracking are bad, so it could also be beneficial for the user. So for instance, if you want to enable parental control on the device, or if you want to get the products that are of more interest to you, you could be using touch tracking to enable that as well. So this way of tracking is particularly dangerous in our opinion because of the fact that it's not that difficult to do. So it requires no specialized hardware. So many of today's devices come with obviously the touchscreen touchpad and also a host of other sensors which could be used easily to track users. Now, one particular thing here is that the apps do not require any special permissions to use the fine-grained information from these sensors. And this is what could be exploited by these apps to actually track users, as I mentioned, across multiple devices or multiple users on the same device. So the goal of our work was to actually show that touch tracking is feasible. And so there are two parts. One is that we wanted to show that these touch gestures, by that I mean swipes or taps, or any other gestures we use on devices with a touch screen, are highly unique. And here here, it's a little bit different from tracking through other mechanisms, for instance, browser fingerprinting, because a browser profile, if it's unique, is enough to track users because it remains static over different sessions. But user behavior is inherently stochastic, so there will be small variations. So just showing that the gestures are unique is not enough. We also wanted to show that it could be used to re-identify users if the user come back in a different session. So we wanted to be able to show the feasibility by actually quantifying the information contained in these gestures. So the second part of the talk, I'll talk about this quantification methodology. So as I mentioned before, there are several scenarios of touch tracking. So single device, single user, single device, multiple user, and cross-device tracking. But our work is currently focused on the first two things. The last one is left as future work. So here's a sort of flow diagram of how we achieve this. So we first have this quantitative methodology of quantifying information contained in gestures. We then developed this special purpose app called TouchTrack to collect data from users, which runs this touch analytics service in the background using the quantification methodology. We then collect data from users, we evaluate the quantity of information contained in these gestures, and finally we display these results to the users. So in more detail, so we first have this TouchTrack Android app, and we focus on 4 different kinds of gestures: swipes, taps, handwriting, and also keystrokes. And then we collect features, which we do a comprehensive list of features that are available in the literature. And then from those features, we narrow down highly identifying features. We then plug them into this quantification framework, which gives us uniqueness results. So a little more about this quantification framework. So we actually assess the uniqueness of gestures at multiple levels. At the lowest level, we want to find out if a single feature extracted from a gesture could be highly unique or identify a user. For instance, one user might have a particular tendency to exert more pressure on the touchscreen. Then we go to a next level where we would like to find out the uniqueness of a particular sample of a gesture. So one complete swipe, which means all the features contained in that swipe. Then we go to the next level where we have multiple gestures, multiple samples from the same gesture, which means, for instance, multiple swipes. And at the highest level, we have multiple samples from multiple gestures. So at all levels, we would like to quantify the information contained in these gestures. So for quantification, we use this information theoretic measure called relative mutual information. So in the denominator, we have the entropy of the whole user set, and every single gesture that we obtain would reduce the amount of information required to pinpoint the actual user, which is denoted by the conditional entropy. So this measure is between 0 and 1, and the reason why we use a relative measure instead of an exact measure is because through our user study, we had different number of users for different gesture types, and we wanted to have one scale for all of them. So this conditional entropy is actually calculated from the empirical probabilities from our data set. So for the single feature, we find out the proportion of times a target user is likely to exhibit a particular feature value. For sample, which means one feature vector from one gesture, we've find out the proportion of times the target user exhibits a similar feature vector. So here we can't have an exact similarity because of the number of dimensions of the feature vector. You wouldn't have an exact match. So we instead use a similarity based predicate here. Likewise, for samples from multiple samples from the same gesture, we find the number of times the target user would exhibit a similar average vector. So in this case, we would combine the feature vectors from multiple gestures and take the average and compare against the user's data that's already stored. And likewise, for multiple gestures, we will find the proportion of times the user will exhibit the similar average feature vector across multiple gestures. So now is the last part of the talk, which is about the TouchTrack app, experiments and results. So we built this TouchTrack app with 4 different games, one for each gesture. And some of these games are available in the Android Google Play Store. We had to customize them for our purposes. So the second snapshot here is the game Lexica, which asks the user to find words by tapping on different letters in that grid. So that is obviously to check, to grab this tapping information. The next one is 2048, and this is for swipes. So with these different apps, when the user uses them, we can then display the result of uniqueness. So this one here shows the uniqueness of swipes, taps, and also at the end we have a more detailed information, detailed results for that user to see how unique their gestures are. So we actually uploaded this app on Google Play Store and were able to collect data from about 89 users and more than 40,000 samples. As you can see, the samples are not uniform across multiple gesture types, and that's probably because of which games were more entertaining and which games were not that entertaining. After we obtained this data, we went to feature extraction. So what we did for that, we divided the data set into a training set and a test set. And so we wanted to select features that satisfy 2 criteria or balance 2 things. One is the relative mutual information, which I mentioned before, which is to show how unique individual gestures are. And the other thing is true positive. So we would also want to correctly identify returning users. So true positive here means if we have a test sample and the only user that is returned by our framework is the actual target user, that's considered as a true positive. So we selected all those features which satisfied or which gave the best balance between these 2 criteria. And obviously if we increase the number of features, the relative mutual information increases, but also the true positive rate decreases. So we needed to have that balance. So on to the results. So for single features, we found out that the area, or in other words, the size related features were the most highly identifying ones. And these are related mostly to the swipes. So the way we swipe, the area covered by our swipes is quite highly identified across users. For for single samples from gestures, we again, for single samples from gesture, we see that handwriting and swipes leak the most amount of information compared to taps and also keystrokes. And for multiple samples, the result is quite similar. We have handwriting and swipes leaking the most amount of information. Combining all the types of gestures together, we see that if we combine, if the tracking service is combining information collected from all different types of gestures, then it can reveal about 99% of information. And the most revealing combination was swipes, handwriting, and keystrokes. So, as I mentioned before, the previous results are more around the uniqueness, so we also wanted to find out if we could re-identify users. So we did this experiment, and then we found out that the combination of swipes plus handwriting is the best combination in terms of both the uniqueness of information and also the true positive rate, which relates to correctly identifying returning users, and also has the least false positive rate. Before I end my talk, just a slight discussion around, if some of you are familiar with the field of continuous authentication, so there might be some similarities in your mind. So there are some differences here, or some stark differences. The first one is the obvious aim. The aim of authentication is to verify a claimed identity, whereas in tracking you are trying to track users. So in an authentication system, you would have an input sample, and you know which target model to test against, whereas in tracking you may or may not know the actual identity of the user, and you still want to be able to re-identify users. Similarly, authentication needs to be highly accurate, which means high TPR and FPR and low FPR are critical. In case of tracking, that is not that a critical thing. So to conclusion, we have demonstrated that touch-based tracking is feasible by showing that it has could be used to track, re-identify users, and also these gestures contain a highly unique information. We have left this cross-device touch tracking as future work because we would need to find out those features that could actually be consistent across multiple devices. Thank you.
Questions?
Is this working? Yeah, thanks. Really interesting talk. Questions, you said approximately 89 users. I'm not sure what approximately means when it's 89. But how confident are you that this expands to more than 89? That seems like an awfully small number to be giving the number of digits of precision that you display on some of the later slides. And the other question is, could you review your threat model for me? I sort of am having trouble understanding why, if someone has the ability to install this software, to identify you. Thank you.
For the first question, so we did this with 89 users, but obviously as more user comes in, we get more refined information. But the main point here was that because users' gestures are unique, we would see a similar trend. We would probably require more samples if we get more users to correctly re-identify the target user. For the second question, so I think a best example here would be if you're using a browser application on your mobile phone, and that application, so whatever websites you try to use on your through that browser, that will be able to know if it's a returning user or not. So you're able to track multiple, so you're able to track users across multiple sessions. If you have a particular app, it could also be used as an additional factor to track the user. So if you, so you could think of as adding more information that could be used to track users, with say some other information that is available already to track users. Does that answer the question? One question.
Maybe I missed this, but could you talk a little bit about what the feature space looks like and how you made those selections?
So for each of these gestures, say taps or swipes, we collected the different features that were identified in related studies on, say, continuous authentication. And we had a comprehensive list of them. Then we ran them through this algorithm called minimum relevance, maximum, or maximum relevance, minimum redundancy, which basically weeds out all features that are somewhat correlated with other features. And so we take the one that is maximally identifying, and then any other features that are basically giving you very similar information are not selected. So we go through this process.
Okay, so we're running a bit out of time, so just maybe one very short question.
No, it's just how do you correlate, for example, devices? Because when I'm using on my smartphone, I'm just like one-handed. For example, on my iPad, I may use two hands. Or how does the among devices work? Because the gestures may change, or the way I interact with the device may change.
Yeah, so those would be like interesting use cases to study. What we wanted to do was to see how, if you use in a typical way, would be used to track use. But those like different use cases are interesting to look into. We didn't look into those.
Okay, so let's thank the speaker. And the next talk is about, it's by Pavel Lifshitz from Technion, and it's Power to Pip All, Inference attacks by malicious batteries on mobile devices.
Hi, thank you for the introduction. So I'm here, I'm from the Technion. I'm here to present Power to People, malicious battery attacks on mobile devices, a work we did in collaboration with the Hebrew University and UT Austin. So, your smartphone is running out of battery. How does that make you feel? If you panicked, you're not alone. 90% of people do. There's a name for this condition. It's called low battery anxiety. If you suffer from low battery anxiety, once your battery is below 20%, you might exhibit symptoms like ordering in the restaurant just to use their power outlet, or secretly borrowing someone else's charger. Wouldn't it be great if you could charge your battery just once a month? We can't. There's no Moore's law for batteries, meaning the battery technology is improving much slower than the growing demand for power. This is mostly because of physical and electrochemical limitations. So, instead, we try to make our batteries smarter. We add smartness by adding sensors like current, voltage, temperature, and a special chip called fuel gauge, or battery management system that monitors and reports information. Why do we do it? First, for safety. We can control battery temperature during charging or regulate the voltage during battery operation. Second, we extend the battery life, for example, by better controlling the charging process. Third, we get better performance. Let's see a couple of examples. Software-defined batteries. an SOSP paper from Microsoft and Tesla showing hardware prototype and Windows driver implementation of management system for heterogeneous batteries that achieve better energy density, charge speeds, and longevity. Another example is in all of your laptops. For over 10 years, there exists a widely adopted spec of smart battery system. Now, let's take a look inside your smartphone battery. We can safely assume that what we have in laptops today, in just a few years, would be in the smartphone. We already see between 3 to 4 terminals which serve the smart function. It can be a temperature sensor implemented by a thermistor, NFC antenna, but it can also be a more complex feature like battery system indicator. So, what do we have? Smart batteries that can be programmable, will be programmable. Wait a second. Isn't that a privacy threat? It is. Our paper lays out the methodology for mounting attacks from malicious batteries. In it, we show that if the attacker gets on your battery, he can discover your browsing history, know which applications you run, what you type, when and where you take a picture, and your communication profile, the time of your phone calls. In this talk, I will describe the general scheme for malicious battery attacks, show examples of keystroke inference and combination of multiple attacks, and data exploitation mechanism via the browser. Of course, I encourage you to read many more details in the paper. There are 2 stages to the attack. An offline learning phase where the attacker builds training set by collecting power trace while performing the target activities, such as web browsing or typing. Here you can see our experimental setup for collecting the power traces. We insert a small shunt resistor between the positive terminal of the battery and the phone, measure the voltage drop on the resistor, and record the measurements at 1 kHz sample rate. Once the power traces were collected, for each type of activity, we train an attack-specific classification pipeline. At the second, online phase, the attacker deploys that pipeline on the victim's battery. Now the attacker continuously monitors the battery draw on the victim's device. The trace is processed by all the classification pipelines of all the attacks independently. Each pipeline watches for the user's activity relevant to it. Once the activity is detected, the pipeline processes the events. It should be noted that events inferred for one attack-specific pipeline may improve the accuracy of another pipeline. Let's take a look at typical application-specific classifier for a specific attack. Such a pipeline comprises 3 stages. Activity detector that makes sure the pipeline is invoked only when there is an activity on the phone. Novelty detector that validates the activity is relevant for the specific attack, and the actual classifier that labels the activity. For example, a browsing history inference attack. In this attack, we want to discover whether the victim is browsing one of the sites in the watch list. The activity detector will determine whether the device is being used. The novelty detector will determine if the event is a browsing event and if this is a browsing event to a site from the watch list. And the classifier labels the event as browsing to one of the sites in the watch list. It should be noted that the novelty detector is the critical part of the inference phase, as we operate in an open world setup, meaning most of the events are irrelevant and must be filtered out. The attacker, however, faces a constraint. The malicious battery, the malicious power trace acquisition and processing device must fit the small form factor and power envelope of the phone's battery package. This constraint limits the signal sampling rate and computational complexity of classification algorithms. The sampling rate also dictates the storage requirement in case the attacker plans to store the whole power trace history of the victim. For all the attacks in the paper, we sample at 1 kHz, and we show that some attacks are possible with as low as 100 Hz. In such case, the attacker can store a long uncompressed power trace inside the battery on an 8 GB flash card. See the paper for analysis of the processing device. Now, let's dive into one of the attacks. In keyboard inference, we are trying to determine what the victim is typing. The general idea is to determine that the victim is typing something, and then try to identify the key presses. So in this case, our novelty detector will detect the key presses. We apply sliding window on the collected power trace. Each window is fed into a binary classifier implemented by convolutional neural network of typical architecture for image classification. So now, for each window, we know if it contains a keystroke or not. Now, we need to group the windows to locate key presses and key releases. This is done by post-processing. The next stage is end-to-end convolutional neural network that performs inference from power trace to characters typed. This time, the window is much wider, such that each window contains multiple key presses, while the key press to infer is located in the middle of the window. The intuition for that is what determines the character is not the shape of the power trace of the given character itself, but the timing of the flanking characters. In the paper, we discuss why it works, compare to other algorithmic methods. We also analyze sources of the leak for the attacks, the robustness, and precisions. By the way, it turns out source for keystroke leak is the capacitive touchscreen and not software. Again, see the paper for details. So what are the results? Average precision is 46%. This number is on par with previous attempts to infer keystrokes from side channel. But key inference on its own is insufficient to really understand what you type. And here comes one appealing point of malicious batteries. We can combine the power of multiple attacks. In this case, web inference with keystroke inference. If you know the site you are browsing to, the problem becomes a closed dictionary, which makes the keystroke inference much easier. So for example, if we know that you browse to Ryanair website, we now achieve 50% precision for top 5 guesses of your flight destination. 40 times better than random. The last topic I want to address in this talk is exfiltration. Data exfiltration from the battery poses a challenge. Once the attacker gets on your battery, how can he get away with the stolen secrets? There are many options, but none of them work. The attacker can transmit using Wi-Fi or Bluetooth installed on the battery, but it might reveal the presence of the malicious battery. Another option is to manipulate the output voltage of the battery, but this would either require an app installed on the phone or can be read by reading the battery percentage from the browser by JavaScript using battery status API. Installing an app is out of scope for our attack because we require no software modification. And reading the battery percentage isn't an option because the update rate is too slow, every 30 seconds. Our key idea is to manipulate the charging status of the battery. It turns out the update rate of the battery charging status is not limited for the in-browser battery status API. The question is how to manipulate the charge status from within the battery. To control those state changes, we place a charging coil, same as the one used in wireless charging, into the battery. So now this allows us to create a new bidirectional covert channel. To trigger the exfiltration, the victim has to visit a sync website that is reading the data. This can be a Wi-Fi gateway at an airport or a conference. First, a visit to such malicious website is detected by the battery. Second, the malicious battery, using charging coil, induces a steady stream of charging events. Now the attacker collects the data using JavaScript utilizing battery status API. This allows us sending up to 1 bit every 2 seconds. This might appear slow, but it's enough to send ID and information like the victim took a photo at restricted place, received a phone call, browsed the blacklist website. The paper contains many more details, various attacks, robustness analysis, why the power channel leaks, and defenses. At this point, I hope I convinced you that malicious battery is bad for your privacy. But I'm sure you feel it's still very theoretical. But think again. chances are you will replace your battery during the lifetime of your phone. This is because your battery has a lifespan of about 300 to 500 charging cycles. The global market for laptop, tablet, and phone batteries is already over $8 billion and flooded with counterfeit products. So if the battery in your phone was replaced, maybe it's already been hacked. By the way, if such hack can affect government agencies, it's not going to be fun. So now, in addition to low battery anxiety, you might have malicious battery anxiety. Thank you, and I'd be happy to take questions.
Questions?
When you do the testing, do you have like only the browser going to its web page with one tab, or do you also do experiments that have more apps open and maybe more background noise?
During the you mean during the exploitation? Yeah. So what we see is that the user-facing application is the most dominant one and has the most effects on the power trace. So it usually is the signal is strong enough in order to detect and be able to classify the action or.
The trained CNN model, is it running inside the device always, right? The classifier that you train. So how complex is it? How many layers? I mean, if it can easily be a large resource hog app, right, in itself, especially in terms of memory. So how practical the attack is actually?
So in our model, we only do inference on. We don't do the training, of course. So, for example, for a keystroke detection, where you want to detect if there was a keystroke, there are 5 convolutional layers with relatively very small input. The input window is 1 over 100 samples. This is because the keystroke is a relatively short procedure. We see it takes about 100 milliseconds for a user, plus minus 30 milliseconds. So the window is small enough. And we have 5 convolutional layers and 2 fully connected layers, and this can easily run on a low power DSP, the inference phase. We calculated it in the paper, so there are details.
Can you talk a little bit about countermeasures? Is it mostly about reducing the accuracy of inference, or is it more about making the exfiltration of inference harder?
Sorry, could you repeat the question?
So can you talk a little bit more about countermeasures? Are the countermeasures aiming to reduce accuracy of inference or making the exfiltration of inference harder?
Yeah. Okay. Thank you for your question. So we discuss mitigations in the paper, but basically it's a trade-off, right? The power channel leaks because you try to be very power efficient. So the extreme case to the other side is you can take a constant power draw, and then your battery will end after 2 hours of usage. So we discuss in the papers different methods of countermeasures, and the conclusion is there is no simple method that can defeat all of the attacks. Some of the attacks, there are methods specific for specific attacks. But usually what we want to to make fail is the novelty detector. So once the novelty detector phase fails, this is the most important component of the attack, because you operate in open world, and we base most of our defenses by making the novelty detector fail. So we can, for example, induce some peaks in the power to obfuscate the power signal.
It seems like you're really relying on battery stability. Firefox a couple of years ago removed battery stability.
But Chrome didn't, and other browsers didn't. And this is related to exfiltration.
Okay, we have time for one last question.
So my question was about countermeasures. So just I was wondering if there is anything the user can do now to as a countermeasure, like switching between applications very often, just to so not waiting for the people to develop countermeasure. Is that something that the user can change in this behavior?
Well, for example, you can the user can run an app that does a lot of calculations, even if it runs in the background. So this would obfuscate the power, but it will drain your battery.
Okay, let's thank Pavel for.
Thank you.
I want to talk to you about some work that was done primarily by my former student Anupam Das, who's just finished up his postdoc at CMU and will be starting as an assistant professor at NC State in the fall. If any of you know of promising graduate students, send them his way. Also with Edward Chu, who was an undergrad at the University of Illinois, and he's since moved on to be a grad student at Stanford. So we've heard a lot about tracking already in this conference. And one of the things that's been happening in recent years is users are increasingly turning to various types of tools to try to limit the people's ability to track them. So Privacy Badger, Disconnect, Ghostery are extensions that keep growing in popularity. And we've even seen these things move into the mainstream. So Brave, they had a bunch of stickers over there. I got one. That is a browser that's specifically designed for privacy and tries to prevent various types of tracking. Firefox Focus is another privacy-focused browser. And then, of course, Apple announced that their new version of Safari will incorporate tracking protection by default. The tracking and advertising industry has not been taking this lying down. They have, in particular, spent a bunch of time trying to figure out how they can track people through other mechanisms than the traditional cookies. So, for example, in 2012, Maori and Shasham developed this fingerprinting technique where you can render a text and use this rendered image as a fingerprint to try to distinguish different devices based on their operating system fonts and so forth. And in 2014, it was found that over 5% of the top 100K Alexa sites were actually using this fingerprint to try to track users. So today, I want to talk about tracking in a mobile browsing context. One of the things that happens is that if you try to fingerprint mobile users using traditional techniques, such as canvas fingerprinting, browser fingerprinting, and so forth, you actually have somewhat less ability to do so, especially in the Apple side of the infrastructure. Apple has relatively homogeneous hardware platforms. They have very fast upgrades in the sense that a very large percentage of the user population upgrades to the latest version. There's more limited ability to customize your browser with font and extensions. And in fact, this was documented in a couple of papers that mobile fingerprinting doesn't work as well. On the flip side, mobile browsers have a bunch of sensors that are embedded in them and that are available to websites. Not all of these are available to websites, so we particularly focus on motion sensors. So motion sensors are ones that are accessed through the Device Motion API. This is the standard API implemented by all mobile browsers. If you want to check it out, you can actually just go to this URL on, if you have a smartphone. I won't mind. I won't be offended. And this API provides access to the accelerometer and the gyroscope. And most modern smartphones have both. Some cheaper, older smartphones just have the accelerometer. One interesting thing that you'll see if you try this is that this API is available to any web page that you connect to over your mobile browser without any authorization. There's no permissions, nothing. And so if you go to this site that we set up for you, in this site you are able to, we show you the accelerometer values that you have. But of course, that's just because we try to make it visible. It is very easy to collect these sensor values in the background and do anything with them. And those of you who did try this web page, you might notice that even if you leave your phone stationary somewhere on a desk, these values keep jumping around. There's a bunch of noise that happens among the readings that you get from these values that comes from various physical and environmental factors. So the question that we're looking at is, can you use these readings, essentially the noise that is created by the accelerometer readings, to identify individual devices through the application of machine learning? So our workflow is basically we take training traces that are collected just by taking them through the Device Motion API. We extract some features through basic signal processing, something like mean, variance, the power of the signal, and so forth. We then put them to develop a classifier using supervised learning, so we know which device generated which trace. And then we can take a test trace and try to classify it. So this is the overall approach that we're taking. In fact, this is the approach that's been taken by a few different research studies with various results. So we had a paper a couple of years back that did this on kind of a smallish lab study that showed that we had pretty promising results for being able to fingerprint motion sensors. One of the things that we wanted to in this paper is really dive into the understanding how well this would work in a real-world setting. So the first thing that we did is we worked with a much larger data set than previous studies, and we also wanted to test the environment in a much more realistic scenario. This led us to then need to improve the algorithms that we had used before to adjust them to use more types of data. We developed a special voting algorithm to improve the classification accuracy and to adjust them to an open world scenario. And then finally, what we did is we looked at developing defenses for this kind of fingerprinting. So let's start with our initial study. So we recruited users through an email survey and by sending out paying people through Mechanical Turk. We collected, each user would use their own personal smartphone to go to a web page that we set up, and that would allow us to collect a bunch of samples of their accelerometer readings in two settings, with the phone being on the desk and the phone being held in their hand. And we got 294 users traces in the on-desk scenario and 256 in the in-hand scenario. We tried a few different classifiers to work with the features that we had, and we were able to get pretty good results. So we had, out of the 300 users or so, we had 86% accuracy in the desk scenario, and not quite as good in the in-hand scenario. But it turns out the results were a little too good. So this was the way that we were first analyzing data. We had the users collect 5 samples with a phone in their hand. Then we had to put them down on the desk, and they collected 5 samples on the desk. We had to then pick it up again, collect 5 more samples, and put them back on the desk. And then when we evaluate, say, the in-hand scenario, we take the 10 in-hand samples, we randomly split them between the training and testing set, and we evaluate the accuracy of our classifier. When we tried an alternate approach, where we used the traces from the first so-called session, the first 5 samples for training, and the second 5 samples for testing. And turns out that our accuracy dropped significantly. And this was a very interesting result because it highlights some of the difficulty in trying to evaluate these kind of attacks, especially in the lab setting. There's a number of studies that try to look at, including ours, that look at accelerometers in the lab. And so the question is, are they picking up kind of very transient fingerprint properties where maybe just the way you place the phone on a desk creates an effect that you can observe? Or are they picking up something that's more inherent to the phone? So working with this new experiment design, we spent some time trying to improve the fingerprinting accuracy. So we used a bunch of new features. We had some processing to extract not just the raw X, Y, and Z values for the gyroscope, but also the azimuth and inclination to kind of show the position that you hold. Also looked at acceleration without gravity to try to factor out the large magnitude of acceleration that might have been confusing in machine learning algorithms. And then we developed a special voting-based classifier that boosts the accuracy of our classification. You can find the details of this in the paper, but the long and short of it is that we're able to get 73% accuracy on about 300 people in an on-desk scenario and 60% in an in-hand scenario. So what does this mean? Does this mean that fingerprinting works, fingerprinting doesn't work? Well, 73% accuracy probably isn't all that great all by itself, right? You aren't able to, in a quarter of the cases, you're getting the wrong person identified. But you can actually do some quick back-of-the-envelope calculation and say that if you think about information-wise, we're getting at least about 4 bits of information in hand and 5 bits of information in the on-desk scenario out of this. So then the question is, if you are getting some useful information out of the sensor fingerprinting, and the question is, can you combine this with enough other features that you can extract, such as maybe the user agent, maybe somebody's network location, and so forth, to be able to classify them. And we have in the paper some discussion that looks at some scenarios and how well this works and how well this doesn't work. In the interest of time, I'm going to skip past that and talk to you about some work that we did in the mitigation side. In the mitigation, we did 2 approaches. One is that we obfuscated the signal by adding some noise to the sensor readings. The noise actually has to be correlated so that you aren't able to just remove it by signal processing, though you have to change it across sessions. And there's more details about that I can explain later. And then the second approach that we tried is very simple, where we just quantize the readings. You essentially can think about dropping readings past a certain, dropping all the numbers after a certain decimal, or quantizing them into certain sized bins. And so you can see in the graph here that this does significantly reduce our ability to fingerprint smartphones. But the question we want to look at is, how does this impact people's ability to use the accelerometer in application? And so we tried to figure out what people use this for, and we thought one of the more demanding applications of accelerometers is actually playing, kind of a tilt-based game. So we built one that we had users play. It's a game, in fact, if you really want, after the talk, please, we can go to this URL and you can try this game on your own phone and see how you like it. What we had is we had users play this game in a normal setting where they were getting the raw accelerometer data, in an obfuscated setting where we added noise to the data, and in the quantized setting where we removed the last few bits from the data. We didn't tell the users which setting they were on, and we randomized them. And then we asked them how easy it was to control the phone for a subjective metric. We also measured how fast they were able to complete each level. And there's details about various analyses that we did of the results in the paper again, but the TLDR of it is that there was, with a study with 400 users, we found no statistically significant differences in either the objective or subjective metrics. So there was not an impact that we could see from applying this countermeasure. So in conclusion, our results of our work are a little bit nuanced. We showed that as compared to some previous work, the ability of applying sensor fingerprints in the real world is more complicated. It's more difficult to get useful results. On the other hand, there's still useful information that trackers could extract from these kind of sensor fingerprints. And we showed that you should be able to mitigate these attacks significantly with a minimal utility loss. One last thing I want to point out is that we have a paper that was just accepted into CCS where we show that not only could they be, but people are in fact using accelerometer data in conjunction with fingerprinting scripts already. So we will present that in Toronto in a few months. Watch this space. And if you're interested in seeing our data or playing this game, you can go to this URL. This will be a permanent URL. The short URLs will disappear in a couple days. And I'd be happy to take some questions.
Hello. Thanks for a good talk. Just about the classification problem. So if I understand it correctly, you have a separate class for each of the 294 users, or
A separate, sorry?
separate class for each of the 294 users?
Separate task?
Yeah. So separate class for each of the 294 users. If you want to test if, to track users, you have your classifier. What is the positive class in that case?
I'm not hearing the word. Is it a separate?
Class.
Class.
Yeah.
Yes, I have a separate class for each of those 294 users. What was the second part?
And so how would you then measure the accuracy of the classification? If
the accuracy is just the average accuracy, so the percentage of time you could say for each user what percentage of the time do they get classified into the correct class, and then you can average it over 294.
Two questions. First one, how much difference does the sample rate make to the accuracy?
Can you speak up a little bit, just a little harder?
How much difference does the sample rate make to the accuracy of?
We did some analysis of this in our previous paper in CCS 16. The sample rate does have some impact. It's not a dramatic difference.
And second question related to that, if you use the native APIs rather than the browser APIs, do you think it would be more accurate? Because I believe that the browser actually rate limits the
Yeah,
sample.
it's a good question. The native API does sometimes support a higher sampling accuracy. We have not done this study because our focus was, especially in this paper, was in fingerprinting in the context of web pages fingerprinting you rather than devices doing this. But that's an interesting question. Unfortunately, our data collection methodology doesn't allow us to use a native API because we just ask people to use the web page, but maybe some lab study could be an interesting follow-up.
Yeah, about the mitigation strategy. Would that have an impact on applications such as maps or running applications if the error kind of compounds over time, or do these applications correct with the new GPS and it wouldn't be?
That's a good question. There's... You can get closer to the mic. Okay. That's a good question. If you were in running applications, sometimes you do step detection, and I'm trying to remember. I'll have to answer it offline. We had one test with step detection, but I don't remember the results.
So we have time for one more question. Okay.
Hi, thanks. I'm wondering whether the mitigation of dropping digits is effective enough, and can you still fingerprint users based on kind of how they use their phones, like on the behavioral stuff?
Oh,
I don't know, like how this mitigation, how effective this mitigation is.
Are you asking how good the mitigation is? How we can evaluate that, or?
Sorry?
Are you asking about the quality of the mitigation?
Sorry, I'm wondering how good the mitigation is of just cutting the precision of the values. Can you still fingerprint users if you do this kind of mitigation? Like how effective it will be?
Our main finding is that you're still able to get some better than random fingerprinting of people, but you get significantly less information. I haven't computed the information content of that, but actually I can do that pretty quickly and get back to you.
Okay, thanks.
I have one final question. Can you provide some spoilers about which companies are doing this in a while?
Which what?
The companies using that sort of fingerprinting technique in the wild.
Oh, which companies are doing this? Let me just keep people in suspense until we put our CCS papers out. I think one thing I can say is that we noticed that among other things, companies that are trying to do bot detection, that try to analyze whether the click came from a real person or a bot, are among the people doing this.
Thank you. Let's thank Nikita for...
Characterizing media exfiltration from Android apps. So multimedia sensors on our phones have given rise to this persistent rumor that our mobile apps are constantly watching and listening to us all the time. We've all heard stories where people talk about seemingly random conversations with specific topics, and those topics come up in tailored ads later on their Facebook or elsewhere in the internet. In some concrete examples, Silverpush was embedding ultrasonic beacons into TV advertisements for devices to pick up on for cross-device linking. Facebook has filed patents to recognize user emotions as they scroll through their feed. There was an example of a soccer app that was using the device microphone to listen for unauthorized broadcasts, then using that location data from the device to pick up on where it was coming from. And there have also been examples of photos being taken surreptitiously by shrinking the preview window down to a 1x1 pixel. In general, companies have a lot of incentives to understand and control their users better. But in general, media surveillance has so far been anecdotal. So a few of the goals of our study are to identify and measure media exfiltration at scale, meaning that we use a large number of apps and we also broadly cover app stores. And in this study, we focus on exfiltration over the network as opposed to privacy implications from app access to the hardware itself, such as device fingerprinting and location tracking. And we also consider whether the exfiltration is a leak, that is undisclosed or unexpected. We're also interested in how apps use sensors in regards to permissions requested and APIs that are called. And we're also interested in whether these are happening from the first or third parties. So I talked a little bit about our motivation, and next I'll move on to the threat model of the current Android access control mechanism, the methodology of our study, aggregate results from our static and dynamic analysis, 2 interesting case studies that we uncovered, a discussion of our limitations and recommendations given our findings, and the conclusions of our study. So the current Android access control mechanism requires certain APIs to require permissions before code is allowed to execute, and this protects sensors from being accessed by apps that don't need it. These permissions are requested at install time for API levels prior to 22 and at runtime after level 23, meaning that the permissions are asked for before the code that requires them is called. So in our study, we specifically look at the permission model for the camera and microphone hardware access. So why aren't permissions enough? First of all, they're incomplete. There are no permissions that are required to capture the app screen. Secondly, they're coarse-grained. Permissions are granted at the app level, meaning that third-party libraries that are imported into that app also get access, and users don't know when apps are using hardware. If I were to grant microphone and camera permissions to Instagram to record and post a video, they would have the ability to be doing that 24/7, and as a user, I have no idea when they're using this specific hardware. And there's also a lack of visibility and control. Users don't have knowledge of or control over media that might contain personally identifiable information as it is exfiltrated over the network. And once an app is granted permission, the permission is granted forever. It's not really reasonable to expect users to keep tabs on the permissions that they've given apps, especially when those permissions were granted at install time or when they first interacted with the app. So when looking at media exfiltrated, we determine whether the media is suspicious or unexpected. And to do this, we ask 4 questions. Users don't expect media shared outside the primary purpose of the app, and so that presents a privacy risk. If undisclosed to the user, not only is it unexpected, but it might also violate privacy laws. Many pieces of recent legislation, notably GDPR among others, require detailed descriptions of PII that is collected and used. Media shared outside the normal behavior of apps that serve similar purposes is a good indication that it might be suspicious. And lastly, eavesdroppers can easily observe sensitive content if it's unencrypted over the internet. So if any of the above questions is a no, then we consider it a leak. So given the motivation and the threat of this issue, we developed a methodology to filter apps, collect traffic, and characterize media exfiltration according to this pipeline. For our set of apps, we chose a combination of popular, new, and random apps from 4 Android app stores, Google Play, and 3 popular third-party app stores. And we see whether they call camera or audio permissions, and this totaled 17,260 apps. We used a large number of apps and samples from different stores in order to perform our experiments at scale and to achieve broad coverage of Android apps. Our second step is static analysis, which helps us understand the privacy implications from app code. Our static analysis consisted of permission analysis and media API reference analysis. Permission analysis consisted of the camera and record audio permissions, and we looked in each app's Android manifest XML file to see if they asked for any of these permissions. For media API references, we looked at the standard way of using the camera and recording audio and the video that's outlined in the Android SDK, and since there isn't a standard way of doing screen capturing, we use the straightforward code for programmatically capturing screenshots, and we decompile the apps to search for these method calls. Lastly, for media API references found in third-party libraries, we rely on third-party package names and again search for these method calls. Our next step is dynamic analysis. So why is dynamic analysis necessary? It helps us detect whether media permissions are actually used, since media APIs might be in dead code paths and thus never invoked. And it also helps us detect dynamically loaded or obfuscated code that might not have been picked up by static analysis. So our dynamic analysis test environment consisted of 10 real Android phones, 6 of which are pictured here, and each phone interacted with apps using Monkey for 5,000 events. and we recorded the network traffic using a man-in-the-middle proxy. For detection of media in network traffic, we use a series of 2 steps. First of which is extraction using file magic numbers, which signify the beginning of file headers. For example, JPEG files will always start off with FFD8FF. This chart shows the types of media that we are able and unable to detect, with the bold being those that can be natively produced by Android. This method gives us false positives, so those require manual checking. Our second step is validation. So how do we know that we capture a majority of file types? We use ground truth information generated by a test app that we developed, and we also use well-known benign apps that we expect to send media over the internet, such as Imager, Giphy, SoundCloud, etc. And we also verify detected leaks by manually interacting with the apps and replicating them. So through this pipeline, we're able to arrive at our actual media leaks. So from our static analysis, what do audio and camera permissions versus actual APIs look like? So in this chart, the blues are audio, the oranges are camera, the darker bars signify permissions, and the lighter bars signify API calls. And the y-axis is the percentage of apps over the App Store set. So we find that overall the app stores, there's a significant number that call audio and camera permissions. We also find that apps tend to be over-provisioned in their permissions, meaning that a lot of apps are asking for permissions that never get used. We also find that in the Me.com and Google Play Store sets, they tend to ask for permissions and call APIs more frequently than ANSI and AppChina. And we also find one exception where the API calls for the audio in the Google Play Store were called more frequently than permissions were asked for, meaning that some of these apps are buggy since they can't execute that code without the granted permissions. So for our dynamic analysis results, we found 21 cases of detected media, and 12 of these are considered leaks according to our previous criteria of being unexpected or unencrypted. And 9 of these cases were shared with third parties. So our first case study is photography apps. We found that a slew of apps that do photo editing do their photo editing on the server side, meaning that the photo is sent to the server to get processed. And this is done without any notification to the user. In many cases, the apps have no other functionality that requires an internet connection, such as social media sharing or posting to a public feed, or even downloading new photo filters, which gives reason to believe that users reason to believe that the photo is never leaving their device. In 5 of the apps, the privacy policy vaguely discloses collecting private information, including photos, and one of the apps didn't mention this at all. Our second case study is screen recording, which is something we hadn't expected at all at the beginning of our study. We found that GoPuff, an on-demand delivery app, was sending screen recordings of user interaction where PII was exposed, in this case a zip code, and this was leaked to a third-party domain belonging to Appsy. Appsy is an apps analytics platform that touts screen recording as a feature and places responsibility on developers for hiding sensitive views. However, we find that few apps actually use the API method of doing so. Out of the 33 apps in our app set that use the Appsy library, only 5 called the method. There's also a server-side way of hiding these sensitive views, and it's unknown how many apps use it, but in a conversation with the GoPuff CTO, he didn't even know it existed, so we responsibly disclosed this behavior to all applicable parties, and GoPuff pulled Appsy from their Android and iOS builds, and they also updated their privacy policy accordingly. Google reviewed GoPuff and Appsy and took appropriate actions according to the statement they gave us. And after some back and forth with Appsy about the privacy implications of this behavior, we were ultimately met with no response. So a couple of the limitations of our study are that we don't detect translated media formats. So for example, if audio is transcribed into text and that text is sent to the server, we don't detect that. We also acknowledge that controlled experiments don't replicate environmental conditions such as voice triggers or facial recognition. And we also don't detect the intentional obfuscation of traffic, although we are able to bypass TLS encryption using Midim proxy. So our work was covered a bit in the press, and it was motivated by this question: is your smartphone spying on you? On one hand, many were relieved that we didn't find cases of audio files being transmitted. However, the screen recording behavior was disturbing enough that many still constituted it as spying. So given this type of alarm, Access to the screen should be protected by the Android operating system, like the camera and the mic hardware permissions, or users should at least be notified and be able to opt out of this kind of behavior by not installing the app. And furthermore, main app and third-party permissions should be separated, as users may have different behavior in granting these permissions if they have more granularity as to what these permissions are used for. In conclusion, we find that most apps tend to have over-provisioned permissions, meaning that they're susceptible for abuse from third parties. We find 12 cases of unexpected or unencrypted media, 9 of which are shared with third parties. And we also find a case of screen recording video that was sent to a third-party library with sensitive input fields in the video and with no permission or notification to the user. For more information and our dataset, you can visit our website, and that's all. Thank you.
Okay.
Thanks for your talk. So you looked at both the static analysis of what API calls you could find and also the dynamic behavior. If you correctly said that if you see an API call in the code but don't observe its behavior, it could be a dead code path or something. But it could also be like a backdoor or something that's triggered under some sneaky circumstance, and that would be really interesting to look into. So if you saw any apps that had a call to use the camera, but it never seemed to actually use the camera, that might be something to look into and see under what circumstances would a code path get executed to actually make the camera.
Yeah, definitely.
Yeah, about the over-provision permission. So you use Monkey to use the apps, right? To tap on the app. So I wonder to what extent you have, I mean, the Monkey doesn't completely explore the full functionality of the app. So I wonder to which extent maybe some of these permissions are used in options or execution paths that the Monkey didn't happen to stumble upon. So I wonder to which extent you can be confident about this over-provisioning and what is the possible error due to the use of the Monkey in the experiment.
So the over-provisioning of apps that we were looking at was based on static analysis, so based on the API call, whether it's called in the app code.
Thank you.
Did you find any sort of genuinely malicious type behavior, like in your screen editing, in your image editing app, for example? Was it the image that was edited that was sent to the server, or was it something else, right? I mean, you can imagine trying to detect the sort of really, cases where the app has no need to behave in a certain way, but yet does.
Right. We didn't find like malicious behavior per se. It was just more like unexpected, like for the screen recording behavior, it was like sent to a third party which users wouldn't expect, and that could easily be, yeah.
Okay, so on the screen capture kind of side of things, is it possible for app A to capture a screen of app B or not? Because if it can only do a screen capture of its own app screen, of course it could just send the data off remotely and reproduce the screen capture on a virtual machine instead. What's the risk with the screen capture in that scenario?
I don't really understand the question.
So I think that what his question is about is whether the screen permission is basically allowing you to break the Android sandboxing and see into what other applications are, the UI of other applications, besides the one that is requesting this permission. But yeah.
Oh, no, it's in the foreground. So there's another API, the Media Projection API, that allows you to do that. But in our case, we were looking at the one that doesn't, like the method that doesn't require permissions.
Yeah.
And it only captures the app's foreground.
Okay, so that seems much less scary than being able to capture arbitrary screen.
Yeah, well, there's like other cases where there's like a lack of intent. For example, if you start typing a message into an app that's and then decide not to send it, for example, and that video is sent off to a third party, or like passwords and credit card information that could also be sent off to a third party.
Okay, thank you.
Okay, one final question? No? Okay, so in that case, let's thank Helene. And I have a couple of announcements. Basically, this is the last session for today. And just a few notes. Basically, if you go to the website, you can actually see the menu that we'll have for today's banquet. And you should remember to bring the color paper, because this is going to be used for your menu. And also you can find there the details about how to get there, and it's basically within walking distance. It should take like 12 minutes. Okay? Thank you.